Hi, welcome to the week 12 session. In this session, we will cover the field effect transistor. We'll just give you an overview. We will not dig into detail and analysis in this transistor. But it's good to know some other type of transistor, especially the FET transistor. So field effect transistor, we usually call them FET, as in short for the field effect transistor. So there are two main groups for the FET transistor: the JFET, junction field effect transistor, and the MOSFET, metal oxide semiconductor FET transistor. And the purpose of this lecture, we will focus mainly on the JFET transistor. But whatever we cover on the JFET will also apply on the MOSFET. So there is some differences in the small differences in the structure, but they mainly function the same. So the main advantage for the FET transistor is that it's has extremely large input impedance. So why extremely large input impedance? You know that when we say that a device has an extremely large input impedance, it means that it has a very sensitive input, and it consumes very low energy, because only very small current is required to operate this input. So FET transistor is mainly suitable for functions that require high input impedance or high input resistance. One of the good example is switching. So FET is very good switch. It can switch very quickly between on and off. So where we can use this application on such, or where do we need this kind of application? A good example is the microcomputer, or the computer in general. In computer, we need switching with a high frequency, and unfortunately, the BJT transistor is not suitable for high frequency switching. So that's why this transistor was invented, and it is suitable for this task. Okay, but let's see what are the disadvantages. It has a smaller gain than bipolar transistor. So when we think of transistor as an amplifier, we mainly tend to use the BJT transistor, as it has much higher gain. And another disadvantage of the FET transistor is it needs more, or it is more difficult to analyze. So this slide shows you the structure of the field effect transistor. So as you can see here, sorry. So this is the field effect transistor. As you can see, we have a semiconductor of, for example, an N-type, and this N-type semiconductor is doped with two P-type region semiconductor on the side, and these two are internally connected. Okay, and we have the one side the drain, and the other side is the source, and here we have the gate. The transistor can be an N-type JFET transistor, or it can be a P-type. So we call this path, we call it the channel. So the channel either can be a P or it can be an N channel. And this is the circuit sample of the FET transistor. For the N-type, this is how you can see the difference between the BJT and the FET transistor circuit sample. It had sharp edges here, and this time we don't have emitter, base, and collector. We have the drain, the source, and the gate. Okay, and this circuit sample for the P-channel JFET transistor. Okay, we will be focusing more on the N-channel JFET transistor. The only difference between the N-channel and the P-channel is the gate, and we will see what is the difference lately. This one gate need negative voltage, while this one can be operated with a positive voltage. Okay, just quickly a comparison between the JFET and the BJT transistor. The first difference between the JFET and the BJT transistor. The JFET is a unipolar transistor, while the BJT is bipolar transistor, which means in the JFET we have only one type of flow, either flow of free electrons or flow of holes, while the BJT there are always two type of flow of electrons and flow of hole, and they are always in the opposite direction of each other. Okay, regarding the terminal, the bipolar, we have the emitter, base, the collector. The source here is equivalent to the emitter in the normal BJT. We call it source. In short, we use capital S. And the base in the BJT that we already know, and that equivalent to the base terminal, we have the gate, and we have the capital letter G to represent the gate. And finally, the collector in the BJT, and that will be equal to the drain in the FET transistor, and we use capital D for drain. Okay, this slide is mainly to show you how this transistor operates and how different than it is. Although we have an N-type, for example, in this example, we have this N-channel, and we have a P semiconductor on both sides. So how you operate? This is a very good example, physical example that we already know. So you know the water tap. This is the source of the water, and here where the water will drain. And we use the tap to open and close the water. This is exactly how this transistor will work. The gate will determine how much flow of water will come from the source and will drain outside. Okay. Okay. So theoretically, how this transistor operate in any BJT, between B-type and N-type semiconductor. If you remember when we talked about the p-n junction diode, we said what happened when you put a P-type and an N-type semiconductor joined together. Okay, remember there is two effects that happens: the depletion layer and the barrier potential. What causes the depletion layer and the barrier potential? Basically, the recombination between free electrons and hole. Okay, so it means since we have a P-type semiconductor here, then between the P-type and an N-type, I have a depletion region here. Okay, and also here. So I have two depletion regions from both sides. And what we mentioned before about the depletion layer, why is it important, the depletion layer? We said the barrier potential is something we cannot control, but the depletion layer, we can expand and we can minimize the depletion layer. How? By applying external voltage. So it means this depletion, this yellow area here, guys, it can be minimized and can be maximized. So we can maximize this depletion layer until we can actually close the channel. So we have control of the flow of electrons flowing from this channel. By expanding the depletion, we can narrow the channel, and we can allow only to minimum amount of electron to flow, or even we can close entirely the channel. Okay, let me show you the next, and here we can make it more clear. So this is a side view of the BJT transistor. So these are the two P-types, you see. In here we have the drain and the source. So this is the depletion, this blue area, from this side and from this side is basically the depletion layer. You see, we can minimize this depletion layer by using an external source, or we can maximize, as in the second graph. When we maximize, this depletion layer will expand from both sides, and as a result, current, the drain current, which we want to control, will equal 0. Where here, where is it minimized, drain current will flow in this circuit. See, so we can make it very small, so the maximum current will flow, or we can make it very large, and as a result, 0 current will flow. Okay. The FET operational region. We have, as in every transistor, we have 3 operation region, but maybe you will find the naming maybe a slight difference. We have the ohmic region, and this is when the gate to source voltage equals 0, and the depletion layer of the channel is very small, and the JFET acts like a voltage control resistor. Okay. Remember, when VGS in an N-channel FET transistor, when VGS equals 0, that's when the maximum current will flow. That means that the depletion layer is very small. Okay. When we start to increase VGS with a minus voltage, reverse bias, that's when the depletion layer will start to expand. Okay. So the ohmic region is similar to the saturation region in the BJT transistor. In second, we have the cutoff region, and this is also known as a pinch-off region. We usually call it pinch-off region, not cutoff region, by the way. Cutoff region, mainly we use it with the BJT transistor. But with the FET transistor, we mainly tend to use pinch-off region to represent this region. And this is where the gate voltage is high enough or sufficient enough to cause the FET to act as an open circuit. So that means the FET transistor will be completely off. No current will flow. So we call this area the cutoff region or the pinch-off region. Okay. The third region is the saturation region. Saturation or the active region. Okay. You can use saturation or active region. And this is, of course, the area where in the middle where the JFET becomes a good conductor, and it is controlled by the gate source voltage. We will see now the curve, maybe that will clear things more. And of course, as in any electronic device, there is a breakdown region. And of course, we don't want the transistor to be operating in this region. The voltage between the drain and the source, VD, is high enough to cause the FET resistive channel to break down and pass uncontrolled maximum current. So if we reach the breakdown down, we will have an uncontrolled maximum current. And usually this uncontrolled maximum current is very high and destroy this transistor. Okay, now this is the characteristic curve of transistor. Now we can see the region of operation we just talked about. So we have the ohmic region here, and we have the pinch-off region where the transistor is off, and here the transistor is fully on. Okay, and we have the saturation or the active region in the middle. Maybe the main difference you can see between this graph and the BJT transistor, you see each curve is controlled by the gate to source voltage, so the voltage between the gate and the source. So remember, this is a voltage controlled device, not a current controlled device. Before, in the BJT, we have base current that control the curve of the transistor. Okay, but here VGS is the controlled voltage. Okay, and as you can see, when VGS is 0, we have the maximum current, while VGS equal -4, we have the pinch-off region. So usually this will be almost 0 current. Okay, so this is usually how we connect the FET transistor. So the voltage here and the current, the drain current, this is the current that we want to control, the drain to source current. and this current is controlled by the gate, and the gate voltage will decide how much current will flow in this direction. Okay, so this current is determined by the gate. If we have VGS equals 0, that's when the maximum current will flow. When we start increase this in minus, so after 0 maybe we'll have -1, then the current will start to decrease, okay, until we reach a voltage that will cause this current to completely stop, so 0 current. So this will be like a switch off. Okay, now there is very few things that is important in this graph. First, there is a point here in every curve. We call it the pinch-off voltage, okay, or VP in short. This VP is the separation between the ohmic region and the active region. Okay, remember the pinch-off voltage separating the ohmic region from the active region. So when this transistor is working on this area, on the ohmic region area, the transistor is basically like a resistor, and we call the resistance of this FET transistor the ohmic resistance. Okay, and it's very easy to be calculated, the ohmic resistor. Let me show you. We call it RDS, and RDS is very easy to calculate. It's going to be the pinch-off voltage divided by the drain saturation current, IDSS. This is the drain saturation current. So at this point we have IDSS and we have VP. So if we want to calculate the resistance of the FET transistor, as I said, if the transistor is working in the ohmic region, it will be acting like a resistor, and the value of this resistor can be calculated. We call it the ohmic resistor, and it's going to be the pinch-off voltage over the drain current, the saturation drain current, the maximum drain current, which is this value, IDSS. Okay. Now we move on to the transconductance curve. The transconductance curve is quite important because basically it shows you the relationship between the input and the output. We have two axes. This one represents VGS, and this one represent the drain current. Okay, so in another way, this is the input and this is the output. So it's the relationship between the input and the output. And as you can see, the transconductance curve is the drain current ID versus the gate to source voltage VGS. So if we read the value of ID and VGS of each drain curve in the previous figure, we can plot this curve. Notice that the curve is a non-linear, because as you can see, guys, by approaching VGS 0, the drain current will start to increase faster. So as a result, we will have this non-linear curve. And this non-linear curve, or if we call this non-linear function, is represented by this equation. So mathematically, this is the equation that represents this curve. ID equal IDSS, 1 minus VGS VP all to the square. Because of this square here, the quantity of this equation is often called the square law device. So the FET transistor, because of this square feature, is often called square law device. So the square of the quantity produces a nonlinear curve. Okay, let's go deeper into the transconductors curve. So in this slide, three graphs. The first graph's A. This is a transconductance curve of the FIT transistor. In this graph, the main supply voltage, which is between the drain and source VDS, is 15 volt. And as you can see for this specific FIT transistor, the VGS off is -4. So this when the transistor is fully off, no drain current, and the drain current is try to increase until it reach the maximum drain current when VGS equals 0, and that will be 10 milliamp. So the two point for this curve is VGS off, and the other point is IDSS, the drain saturation current. Okay. Now, graph C is quite important. This is the normalized transconductance curve. So what normalize mean? Normalize mean that we are graphing ratio, and this ratio is the ID over IDS. That means the drain current over the maximum drain current, and this axis is the ratio of the VGS voltage over the VGS off voltage. So the maximum VGS voltage over the VGS voltage at any point. And as you can see here, for example, at the middle point, the half cutoff point, and cutoff voltage is -4. So the half cutoff is the drain current will be the quarter. Okay, so from this graph, actually we can find the drain current for any VGS voltage. So if VGS voltage is quarter of VGS off of the cutoff voltage, then the drain current will be 9/16. Okay, we will see how this is important in the next example. Okay, let's see this first example. We have a FIT transistor that has the pinch-off voltage equal 5 volt, and the saturation drain to source current is 100 milliamp. So the maximum current is 100 milliamp. So what is the ohmic resistance and the gate to source cutoff voltage? We know from previous slide that RDS equal what? Equal the pinch-off voltage over the drain maximum current, IDSS. Okay, so it means for this example we have 5 volt is the pinch-off voltage, and the drain current is 100 milliamp. So that will give us 50 ohm is the ohmic resistance for this transistor. And second we have the gate to source cutoff voltage. So the required is VGS off. VGS off is always going to be minus VP, and VP, the pinch-off voltage, equal minus VGS off. So very easy, straightforward, minus 5 volt is VGS off. Okay, so second example, we have a FIT transistor, and this time the gate to source off voltage is -8 volt, and the drain saturation current is 16 milliamp only. So the required is what is the drain current, ID, and the gate source VGS off at the half cutoff point. So it's what is required at the half cutoff point. Now we need the normalized transconductance curve. If you remember, at the half point, the drain current is a quarter of the saturation current. Okay, so we will say here that since ID over IDSS is the ratio for the half cutoff point, at the half cutoff point equal a quarter. Okay, so at half cutoff, this is at half cutoff. Okay, so therefore ID will equal what? IDSS times quarter, meaning that will be how much, guys? 16 milliamp over 4 equal 4 milliamp. So 4 milliamp is the drain current at half cutoff point. Now VGS, so VGS over VGS off from the transconductance curve, the normalized transconductance curve, equal 1 over 2. So that will give me that VGS will equal minus 8 over 2. So that will be minus 4 volt. So that's the gate to source voltage at half cutoff point. Okay, so that will be all. Thank you for watching this session.